In the last episode, classical physics reached its first catastrophe. Energy was assumed to be continuous, infinitely divisible, smooth. But blackbody radiation refused to obey that assumption. And now, we arrive at the moment quantum mechanics was born. Classical physics predicted infinite energy at high frequencies, but real heated objects did not emit infinite radiation. So something inside the classical picture was wrong. Max Planck was not trying to create a new reality. He was trying to solve one specific problem: blackbody radiation. At first, his idea looked like a mathematical trick, a technical fix. But the fix was hiding something much deeper. To understand Planck's idea, we need one word first: frequency. Frequency means how many times a pattern repeats per second. If a wave repeats once per second, its frequency is 1 Hertz. If it repeats 100 times per second, its frequency is 100 Hertz. Light is an electromagnetic wave, so light also has frequency. Red light has lower frequency. Blue light has higher frequency. Ultraviolet light is higher still. Classical physics assumed that every frequency could take energy continuously, any amount, as small as needed, as large as the equations allowed. But at high frequencies, this became catastrophic. Too many modes, too much energy. The calculation exploded. Planck made a radical move. What if energy cannot be exchanged continuously? What if energy can only change in fixed packets? A quantum is a discrete packet, not a smooth flow, not infinitely divisible, a smallest transferable unit. Planck wrote the idea in one of the most important formulas in modern physics: E equals h times F. E means energy, the amount carried or exchanged by the system. F means frequency, how fast the wave repeats. The faster the oscillation, the higher the frequency. H is Planck's constant, a fundamental number built into nature. Its value is extremely small, but this tiny number controls the quantum world. The formula says, energy is proportional to frequency. Higher frequency means higher energy. Lower frequency means lower energy. Red light has lower frequency, so each packet carries less energy. Blue light has higher frequency, so each packet carries more energy. Ultraviolet light carries even more. This is the critical shift. Energy does not change like water flowing smoothly. It changes like steps, discrete transitions. Classical physics imagined a continuous world. Planck's formula introduced a different possibility. Nature may not be smooth at the deepest level. This was not merely a new equation. It changed the question of what reality is. If energy is quantized, then reality is not fully continuous. Planck himself did not immediately believe he had discovered a new reality. He treated quantization almost as a mathematical necessity. But nature would not let the idea disappear. This idea later opened the path toward quantum information. Because packets mean distinctions, transitions, states, reality begins to look less like continuous substance and more like structured change. In a deeper foundational view, this is the first hint that reality may not begin with smooth objects. It may begin with distinguishable state changes. But for now, physics had only opened the first door. Planck did not set out to destroy classical physics, but his formula broke one of its deepest assumptions. Energy was not infinitely smooth. Nature had a smallest rhythm. In the next episode, Einstein will take Planck's idea further. He will ask, what if light does not only exchange energy in packets, but arrives as packets? And with that, light will begin behaving like a particle.